I'm going to start by introducing myself. Hello, everybody, and welcome to my meetup. My name is Omid Vahdaty. I'm the founder and CTO of Jutomate. And today we start a series of lectures about petascale data architectures. This series of lectures is designed to be kind of a workshop. So you're more than welcome to ask questions, engage, talk, whatever you need in order to make the most out of this session. You're more than welcome to open your videos so we can see each other and talk to each other and engage. Feel free to ask any question, whether you think it's trivial or not, it doesn't really matter. We're here to help each other and learn from each other. As long as we respect everybody, it should be okay. My team, Tal, is over here assisting me. If you have any questions, please do not hesitate to open your microphones and speak. You can also ask in the chat, but I prefer you talk to me directly. You can even interrupt during. It's okay. I welcome it. The idea is that we have a discussion. And let's start. As people are joining, I'll take the time and slow down a little bit for the first slide. First of all, let's start with the disclaimer. I may not be the very best in the world, but I simply love what I do very, very much. And the lecture is in front of me. On the left screen, I have all the videos of you guys, so you're more than welcome to open your videos and talk to me. And I'll have some background notes on my right to assist me. So you're more than welcome to challenge me on everything I have to say, because I could be wrong. It happens. I'm just a human, like most humans. I make mistakes. And you're welcome to send me comments via email or via LinkedIn. Just add me and we'll communicate. I'm happy to help you for you. A little bit about the community. Big Data Demystified was founded 5 years ago by my company. I lead this community. The idea is to contribute from our experience as Jutomate for the community worldwide. We have about 30,000 followers in over 22 countries. And basically, we every successful project gains us more experience, and with that experience, we share that with the community. All the different content is being uploaded to our meetup community, and the website is called Big Data Demystified. That's one. If you RSVP to this meetup, then you should get a link once the video is uploaded. A little bit about me, and my background. I have over 20 years of experience in the high-tech industry, many startups and enterprises I work with, design some very complicated data architectures. I have a very vast understanding of what it is to be an architect in different technologies, in different verticals, in different types of organization. And in the past, I also developed, I was fortunate enough to develop a database for big data. So most of my understanding of big data comes from this company.
ولی
I have a little bit of background in martial arts, as you can see on the left, about 20 years of experience as a third-degree black belt. I have a passion of skydiving, just my way to have some fun. And I like to lecture and give for myself to the community. I do a lot of volunteering work, and that's me. So a long time ago, here we go. A long time ago,
You're on mute, Omid.
now you can hear me?
Yes.
Yeah, we
Thank
can
you.
hear you.
Thank you very much. Don't know how this happened. Good. So a long time ago, it was very simple. We had a three-tier architecture. We had the web. Can you see my cursor moving?
Yeah.
Thank you. So we have web, we have API and operational DB, and we had the data being replicated to the data warehouse, and everybody were happy. Then came big data, and everything became much more complicated because every now and then your architecture would break, your infrastructure would break. And then came the cloud, made us spin like crazy by learning new technologies and new architecture and everything. Every paradigms we used to work was no longer relevant. And then came the invoice, which made everything even more complicated because now everything now needs to be considered in terms of cost as well. And to make things even more complicating, it keeps growing. And we're more and more and more. And my way as an architect to handle this was to apply cloud methodologies and big data methodologies. And in an essence, to me, this is the definition of data engineering, of modern data engineering. You're more than welcome to open your videos. I encourage this. It would be more interesting on my end, simply because you're on my left. So I Ziv, it will be fun to see your faces nodding. In terms of agenda, this is a series of lectures. It's going to be divided to 3, 4, 5, even 6 sessions, as much as we need. There's no rush. We're not in a hurry. We'll just keep coming and we'll make it work with change agenda, add more content, everything to make you engaged and happy about what you see and hear. So the plan usually is as follows. I usually cover the jargon just to make sure everybody is aligned on what we are talking about, introduce complexity, some use case details, challenges, and then we will talk about implementing that specific use case on several technologies. So we'll have some sort of pros and cons analysis and TCO analysis, and we'll understand holistically how we approach things and what would be the downside or the upside of choosing a specific path. Let's start with some common questions. What do you think is the common challenges of building a correct and efficient petascale architecture? Now would be a good time to open your microphones and videos and engage. Anyone to participate? Fascinating. Okay.
Well, I think
Yes.
it could be the technologies, because some technologies are not made to support this kind of workload.
Right you are. Alibek, am I pronouncing your name correctly?
Yeah.
Thank you, sir. So yes, choosing the right technology and matching it to a use case is what makes a great architecture great. From my experience, most architects don't really have the necessarily broad perspective on a wide range of technologies and don't have a deep understanding, on the other hand, of the business side or how things are working on the business and finding the right fit. The secret sauce is to match a technology to an architecture. And in the end of the day, each technology was created to solve a specific problem, and then it grew from that use case to other use cases. What else? What else do you think is a challenge when you talk about building an efficient architecture?
I think it could also be I think it could also be identifying or limiting yourself to the set of use cases you want to solve for and what you would not solve for initially. I think that could be one of the biggest challenges, to identify the limits of which use cases you would solve for and which use cases would be outside of.
Excellent answer. Thank you.
I believe storage and computation.
Sorry, you believe what?
Storage and computation of this much data.
Please elaborate.
Computations are like processing the data, this much like gigabytes of data. It takes more computation power and infrastructure.
Yes, right you are. That is indeed the challenge, and we'll cover that further on later. Okay, next question. Thank you for your answers. What are your expectations from this workshop? I mean, what do you hope to gain specifically today? If you could share that with me, that would help me fine-tune the message and the lecture. Anyone wishes to share their point of view?
I think for me, it would be what's the latest in the data field, what's the latest technologies, as you said, the most efficient ways to extract and clean and use data, especially on the aspect of cost effective. Because we know we are moving to the cloud, and with that comes a high bill at the end of the month. So for me, that would be what I'm looking for.
Okay, I'll do my best to accommodate your needs. Anyone else wants to share?
Yes, I expect, I hope to have good examples of comparison of different solutions with perspectives of restrictions and costs.
Okay, I'll do my best to support any kind of...
For me,
Yes, please.
I like to know, you have such a large volume of data. How do you organize the data so once get to the analytics and make the analytics more efficient and streamlined, and especially, how do you organize such a big volume of data? And there's a lot of complicated step in between the raw data and to the analytics.
Okay, feel free to challenge me throughout the process. I'll do my best to answer. Let's see if there's something on the chat that people are sharing. Cost and performance, okay, great. Fault tolerance with low latency, comparison of pros and cons, yes, definitely we're going to cover that. Tools and technologies with respect to Azure and AWS. Duh. I'll do my best. Okay, people, we covered everything. Let's be sure. Anyone wants to share their day-to-day data pain before we proceed?
Yeah, my biggest pain on the day-to-day is the speed from the raw data to the analytics. Yeah.
performance.
Yeah, there's so much.
Definitely.
And a
Please
lot of
continue.
data, you can use it without the multiple transformations in between and to get to analytics. Just speed is just sometimes it's just too slow.
Yes, definitely you are in the right place, Don. I'll be happy to explain myself as we go. So let's talk about principles just to align everybody. I'm going to talk really, really fast, but feel free to stop me and ask clarifications. I want everybody to be onboarded here and aligned on the jargon. So when you talk about big data, you talk about the 4 V's usually. This is relatively familiar in the industry. It's a concept that says what's your volume, your amount of data, usually associated with a big wave of data that comes and crushes your infrastructure. And then you talk about velocity. The fact you have 1 petabyte of data is great, but what is the rate of new data coming into a system on a daily basis, hourly basis, minutely basis, or second? The velocity is simply the quality of your data. The variety is the types of data that come into the system. Generally speaking, big data architecture is broadly known in many types of architecture, but they all come down to three layers usually. It's usually called mirror staging and data warehouse, or bronze, silver, gold. But from my experience, it is more accurate or better in terms of performance, maintenance, and cost to talk about 4 layers. And I gave them more described names just so it will be clear. You'll have ingestion, transformation, modeling, and presentation. Where ingestion essentially is your raw data, and transformation is where all the cleaning of your data, cleansing, and transformation of dates, formats, partitions happens. And the modeling layer is where you have all your fact tables and your aggregation tables. And in the presentation layer, you have all the interim calculations you need to optimize access for the BI layer or the end user. An example on AWS would be this list of technologies. Essentially, you have Kinesis or Kafka or Flume to ingest your data, and the storage layer is naturally S3. You can use Glue and Airflow to help you with the orchestration, but at the end of the day, you can use different technologies for different tasks. You can use Hive for complex transformation. You can use Spark for complex modeling. You can use Athena or Redshift for analysis or for even BI use cases. A simple architecture would be use one technology stack across the board from A to Z. If you're talking about GCP, you would be using BigQuery all the way because it makes sense. But there are other analytical databases you should know. I'm going to mention those we're not going to cover today. For example, Cloudera Impala, Vertica, Teradata, and Wood, all perfectly good solution, all capable to support you and your petascale architecture. But in today's use case, I'm going to talk about the top 5 common solutions when you talk about petascale, and we're going to analyze them as we go. In terms of scale out versus scale up, most people fail to notice the difference because scale up is hardly ever used today in today's industry. Scale out is most familiar when essentially you have a data issue and you need more processing power. You just add another machine to your cluster and you move on. A scale up problem, on the other hand, is when you have a problem processing your data, you just resize the machine to a bigger one, adding more CPU, more resources, and more to your price tag eventually. There's no such thing as a bad or good practice in these two examples. I mean, each of them has its pros and cons. If we're talking about the scale out, the advantage would be parallelism, meaning more users, more jobs concurrently. But the downside is power queries and joins. Essentially, a join in big data is an anti-pattern, something we want to avoid at all costs. In scale up, on the other hand, the pros are exactly the opposite. You want to be using power queries, you want to be using joins because it's an architecture designed to support such a use case. But the downside is parallelism. I mean, this is essentially where you first realize in this conversation why matching a good architecture is about matching a technology and a use case. Because if you choose the wrong technology, you won't be able to sustain the workload, and you'll end up in frustration, you'll end up in high costs, you'll end up with lots of maintenance efforts. Jampala raised his hand. Please, jump in, open your microphone and let's talk.
Yeah, sure, thank you. So in scale up, you mentioned like increase resources. So increase resources means what exactly?
Instead of using 10 CPUs and 10 gigabytes per server, you resize the machine for 20 CPUs and 20 gigabytes, for example.
Okay, in scale out, you just use you add the servers, not the CPU.
Yes, another server with another 10 CPUs and 10 gigabytes, for example. Yes, thank you for the clarification. People, please, please, please stop me. Don't be afraid. Don't hesitate. Interrupt, shout, jump, break a bottle, break a chair, do something to bring my attention to you guys. I see your chat, but sometimes it's too late. So please interrupt me. I'm here for you guys. So let's talk about decoupling. Decoupling is essentially an architecture where all your workload is distributed on several servers. This is essentially a server. It has a local disk, but it's a bit confusing. So let's be clear about this. Decoupling doesn't mean dividing your workload to several servers, because the disk is local, and if part of the data is in the same machine, then it's not decoupled, it's only scale out architecture. If you're using external storage, so the data is not in the machine, so I can kill this machine and these two machines can access those data, then it's scale out with external storage. It's still not exactly accurately decoupled. What would make it decoupled? When you have a storage that can be accessed by several computes. For example, let's see if I have an example here. Nope, I don't. So let's fix this slide for you guys. Gonna be a bit trickier, but it should not make it simpler. Oops. This is one, and this is two. Okay, I made it messier, but it should be okay in a second. Okay, what I want to demonstrate is that sometimes, oops, you have several architectures, several technologies accessing the same data. The advantage here, who wants to think of the advantage for me? Who wants to participate while I do this? Anyone? No one? So let's talk about AWS. AWS, for example, is totally decoupled. And why is that? Because they encourage you to write the data once on S3 and essentially utilize that data on several technologies. So instead of Hadoop, forget Hadoop for a second. It will be a bit confusing over here. Whoops. Essentially, you have 1 petabyte in S3. Now it's accessible to both Spark compute clusters and Athena. And why is that good? In the past, you used to do inserts to a database in order to process the data and benefit from the storage optimization that specific technology has. But today, becoming totally decoupled allows you to apply several technologies on the same data, essentially increasing your ability to serve or provide a better service. Is this concept clear?
Yes.
Thank you. So another concept, fixed cost versus pay as you go. Essentially, I gave 2 examples to make it your life very simple. On the left hand, you see technologies like Hadoop and Redshift that you pay fixed cost monthly for a cluster that works 24/7. For example, 10 machines, 10 CPUs per machine, and you pay, say, $100 per month, much more, but say $100 per month, and you can query it as much as you like. On the right-hand side, you have pay-as-you-go technologies like BigQuery from Google and Athena from AWS. You pay $5, give or take, $5 per terabyte you scan. What's the advantage? Serverless, you don't have to maintain a cluster. If you're not querying, you're not paying. Very simple. The knee problem. The knee problem is usually less known because most people don't really get to a situation they have a big data problem. But those who work with big data experience this quite easily. On the left axis is the volume of your data. The more your data increases, the more likely you are to exceed or increase the time to complete the query. However, there's an inflection point somewhere, let's say in the middle, just for sake of argument, where everything will become much horrible. Meaning what? It will stop growing linearly and it will grow exponentially. And then the time to complete the query will increase and sometimes might not even finish. So essentially, for example, running a join on 1 terabyte, which is essentially 1 billion records, will ultimately result in out of memory, out of resources, error, and there's not a lot you can do about it. Is this problem clear? Yes.
Yes.
Thank you for your feedback. I read your chats, not finished and still pay for it. Yes, 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 you are correct, guys. Thank you. Streaming versus batch processing. Some of your workloads can be divided into two options. One would be stream processing, and one would be batch processing. For those who are not familiar, batch is like the traditional way we used to do data pipelines. Essentially, take one big chunk of data, process it. It's more effective, more cost effective. But the downside is latency. On the other hand, streaming is like the droplets you see on the left. You can process them very effectively and very short latency. However, it requires more compute, and that's always something you requires on the business side. For example, achieving a low latency of 1 millisecond is not always important, but 10 minutes delay of the data is more than fine in most cases, because the business doesn't need to be updated as fast as 1 millisecond. Sometimes 10 minutes is more than okay. Okay, whoops. Wait a minute. Yes, so data warehouse versus data lake. This is also a term that confuses most people, but for our intended purposes, let's take a simple definition. A data lake is where everything is decoupled, where the storage and the compute are not together. For example, like we had before, the Spark and Athena, and the storage is on S3. A data warehouse usually refers to a technology where the storage is not decoupled, meaning coupled. So in theory, both can achieve everything, but there are pros and cons for each one of them, and we'll discuss them later.
But the data warehouse doesn't always have the couple technologies. Snowflake, they claim they're decoupled.
Yes, but let me ask you the following. Are you inserting data to Snowflake?
What's that?
I was asking, I was agreeing with you, but let's clarify that for the sake of the discussion. While using Snowflake, are you inserting data as part of your process?
Well, we use Snowflake to store data and do analytics. Yeah, at the data store. Yeah.
So once you insert data, the data is stored on, say, for example, S3. Is the data accessible by other technologies?
Yeah.
I'm not talking about external table. When you insert the data to Snowflake, can you process the data using Spark directly to the storage layer without going through Snowflake?
Well, you can use Spark. You can put SQL in there. That
Yes,
will work.
but it's not the same. The idea is,
Yeah.
It's a bit different. If you remember this slide, the idea is that you put the data in one centralized place and you don't do inserts to other technologies. Simply put a reference to the data set and you work through it. That essentially gives you the advantage of reducing your insert time to 0, for example. And when you want to change technology, you're not bounded by the insert time and migration costs, which could be an advantage in some cases. Does that answer your question? Thank you.
Thank you.
Okay. You're most welcome. Please keep asking questions. Databases. Just to be clear, there are 3 types of families of databases. Operational database, essentially the MySQL, MS SQL, Postgres of the world, usually used for LTP, and there's also NoSQL included in that family, usually designed to help you build an application effectively. However, there are different types of database technologies called analytics, or analytical DB. used for OLAP or different type of querying of data, which is analytical questions. For example, how many users visited my website the last month, which by nature take longer time and process much more data, which could be colder than usual. Archive. Archive is the last type. For example, Hadoop. It's usually something you do or a technology you use to store some data sets that you rarely use. For example, genome database. You spend years collecting the human genome from your society, put them in one place, and eventually some researcher will come and work with this. What characterizes these technologies is two things. One is how hot is your data. The more hot it is, the harder it is. It's more relevant for now, today. The colder it is, the older it is in terms of years. For example, historical genome data from 10 years ago of a specific person. Usually, the second part of identifying a technology in a family is the response time. For example, an operational DB should respond in milliseconds because there's an end user logging into a website and expecting to see a response which is in real time. However, when you research something which is in archive, you should expect running days of hours and days and so on and so forth. Usually, the storage is kept in database in one of the two formats, row-based or column-based. Essentially, I do this color diagram that will help you visualize things. When you insert a row to a row-based database, each row is kept separately. So once you ask an operational DB, give me something about user, all the different attributes can be extracted relatively fast because all the index of the user is here, so everything related to the user is here. But when you ask analytical questions, you need to store everything in a column format to ensure you can ask the following question. For example, how much I sold from this product last year. So this is your sales data. So you need the entire column and you don't need the rest. Any questions about this before I proceed? Okay. We're gonna go a little bit deeper in other aspects of your jargon / architecture. You need to be familiarized before we proceed. So CPU. Usually a cluster is a group of servers designed to perform several or more tasks. CPUs usually allow you to do some multi-threading, some round robin, and distributed workloads. Essentially, a cluster will handle all the nitty-gritty stuff of accepting any job, distributing the job, and utilizing the hardware as much as possible. But you should know the bottleneck is the amount of CPU cores. The more CPU cores you have, the more horsepower you have, the more ability you have to respond to ETL jobs, to query jobs. And essentially, this affects two things. One, parallelism, how many things you can do in parallel, and power queries, how fast you can do one large job. There's always a scenario when you underutilize or overutilize, when you have less resources than required of a thread race. Thread race, that means you're requesting, for example, 100 CPU cores when you have only 70. So the operating system of the servers is essentially in a constant race of managing those resources for you. There are some hardware optimization tricks like hyperthreading that essentially utilize the core more effectively in a ratio of 1.6, meaning for each 10 CPUs, effectively you are on 16 CPUs simply because you checkbox the hyperthreading module in your BIOS on the hardware level. So essentially, a vCPU is a hyperthreaded CPU core. So when you see 20 CPU cores in the background on the hardware level, it implies you have half 10 CPU cores, each of which has an architectural benefit. For example, latency and throughput. Usually, in a big data perspective, you want to aim for throughput because you have power coverage, you have long-lasting jobs. Essentially, time it from end to start is minutes, hours, so latency is meaningless. Concurrency and parallelism also uses threads and by extension CPU cores. Throttling is when you have some sort of rate limitation of requests that applications stop allowing new requests to be processed simply because it cannot handle more. If we have a look at this diagram, essentially a physical CPU core is half the amount of virtual cores. So when you work on AWS or GCP or Azure, and you see the term vCPUs, for example, 8 CPU cores, vCPU cores on your machine, essentially it's 4 physical cores behind it. Usually you shouldn't pay attention to it too much. However, when you talk about big data, every bit of detail makes a difference in terms of performance, maintenance, and cost. So knowing the differences can be the difference between cost-effective architecture to highly inefficient architecture. So essentially, multi-threading would be a Python application or any application opening a new thread and assigning it for our sake and for our intent and purpose, so for our discussion, any new thread you open in your application is essentially assigned to one core, and it doesn't really matter for the application whether it's virtual or not, as long as it's being served. The latency, just to be clear, because this is also a sense of, this also confuses some people. Is the time that spends from the request to the time it actually starts. For example, I ask for my cluster the ability to start my job, 20 milliseconds pass, and then only then the operating system allocates those CPU threads, and then I can work. The throughput is measured in whatever you need, milliseconds, seconds, minutes, hours, whatever, based on your workload. So to compensate for the lack of resources, your operating system applies, applies some sort of strategy to better utilize the lack of resources. One would be round robin. For example, job 1 starts, and then it starts, and job 2 starts, and then it stops again, and you continue on job 1, and then stop again, and vice versa. So essentially, this gives the end user the illusion of concurrency, endless concurrency, but essentially, you're missing the point where the operating system is working very, very, very hard to saturate the hardware and overutilize your hardware, sometimes by an order of magnitude of 400%. Anything bigger than 400 or 500% usually result in a crash. And that essentially is your knee problem where we discussed in the beginning. Are you okay for me to continue? I mean, I don't want to too much push information. It's 54 minutes since we started, give or take 50 minutes. Are you with me? Should I continue or shall we break?
Yes, please, continue.
Yes, please. Thank you. Okay, going deeper on your storage knowledge. So there's lots of jargon about storage. You should know, again, the throughput and latency. Pretty much the same here, but measured in differently, but the concept is the same. There's RAID, hardware RAID, software RAID that simply applies two things. One, redundancy of your data. So if one file is being corrupted, does it have a backup on that disk? This is one aspect. The other aspect would be performance. Essentially, the difference between 0 and 1. 0 is 0 backup, 1 is 1 backup. What does it mean? If you have 0 backup, that means you are using more disks to read-write a file, essentially increasing performance. But if you have 1 backup, that means you're using more disk to save copies, essentially increasing the parallelism, meaning if you are writing 1 file on 2 disks, essentially allowing your application to read from 2 sources at once. Persistence is where your application writes down to a disk. I/O pattern usually affects heavily your performance, whether it's random or sequential. Random, that means you have 1 petabyte and you go all over in your data set back and forth just to get an answer for your query or your job. And sequential is when you start sequentially and run through the history of time day by day, and the order doesn't really matter as long as it's close by one after the other. Decoupling of storage and compute we discussed, cold storage and hot storage we discussed, chunk size. Another aspect of performance is usually correlated with the size of your file. In big data, small files are anti-patterns. Why is that? Can anyone think of a good explanation? Probably most of you know the answer, so please feel free to share.
Cannot take advantage of sequential access.
Excellent. Thank you, Olga. But now let's go one step deeper. How big should the chunk size be to achieve optimal performance? Anyone? 120 megabytes is a good start. Meaning what? Sometimes you can expect to have more performance gain by increasing the size of your chunk size times 2. For example, 256 megabytes, 512, 1 gigabyte. Why is that? Can anyone guess? Okay, I'll give you a hint. It's related to throughput and latency. The time that passes from your request to a file until the fact that it's being actually read is latency. Throughput is the time it takes you to read the file. So if this file size is small, you're paying a penalty for each small file because you have a fixed amount of latency, which is sometimes greater than the time it takes you to throughput read through the file. So essentially, minimizing the amount of file minimizes the amount of latency per file. Is this clear? Yes, no? Very good. Thank you, Usai. Okay, so there are many types of storage options which are relevant for our discussion. For example, local disk, you have magnetic or flash. Magnetic is usually old school disk where you have a needle that goes in circles on your disk to find your data. And you have measure KPI to measure the performance of a disk by using rounds per minute, meaning 7,200 rounds per minute or 15 rounds per minute. This disk is 2 times faster than this one. A flash disk, on the other hand, is more expensive. It's called, for example, NVMe SSD, but it reduces the latency time of seek time throughout the disk. So essentially, it's faster, but it's more expensive. SAN and NAS storage, we're not going to talk. Scale-out storage system, we're not going to talk too deep today, but you should know they exist. Object storage like S3 and GCS you're quite familiar with will be mainly part of our discussion. Local disk. Question. When would you use a flash disk and when would you use a magnetic disk? I mean, both of them are still relevant in today's world. Anyone wants to share from their experience?
The magnetic one is slower, so it's a storage for archiving, and the flash one is for working. It's much faster.
Yes. So essentially, you're correct, both you and Dino. Cost versus performance. Hot data for flash. Yes, but let's take, for example, just to clarify even more. If you have an operational DB such as MySQL, where every millisecond counts to best serve your customer and your application, which disk would you use, flash or magnetic? Anyone? Flash. Thank you everybody for joining in on the chat. Yes, exactly that. But the magnetic, naturally you would use them in archive, but where else would you use them in any other place? S3 storage. Yes,
I mean, storage
exactly.
where you want to hold.
So, sorry, Dino, again?
Yeah, I was saying slow storage where you want to hold large amounts of data.
Yeah.
By slow, I mean where it's not sequential, where you want to download big files and so on.
Yes. What about Hadoop use cases? Spark use cases? Would you use magnetic then?
Yeah.
Why?
I guess because it processes large amounts of data. So Spark, especially, I think it's kind of loading in memory and processing in memory, everything else. So it's suitable for that.
Good. So let's be more precise, though, if I may. When using big data, it's always a discussion, as mentioned by Dino, a balance between cost and performance. However, when you talk about petascale architecture, you have to compromise. So using magnetic disk is an option. And today's disks reach about 20 terabytes of storage per disk. And if you apply a bigger chunk size, let's say 1 gigabyte, you get 20,000 files per disk, which is massive. So let's do some basic calculation. If you talk about, let's say, 10 terabytes, talk about 1 petabyte, that's essentially 1,000 terabytes, and you have 10 terabyte disk, that means 100 disks. So if your workload is analytical and say you have 10 analysts, so the probability of hitting the same disk twice in the same job is dramatically reduced. So essentially, the downside of latency is reduced dramatically. The more disk you have, the less you feel this latency penalty. Does this make sense?
Yes.
Okay, thank you. Just to be clear, so if I took 100 times 100 disks of 10 terabyte and I achieved the 1 petabyte, essentially, and you don't need to worry about latency issues if I have low amount of concurrency. But let's say I don't have 10 analysts, I have 1,000 analysts. What essentially will happen on the storage layer in terms of performance? Hint?
It becomes slower, but you can replicate.
Yes. How bad will it be? You'll have the knee problem on the storage layer, because essentially you're sending 1,000 requests to 100 disks. So essentially it's a 10 requests per disk. What happened for the first request? It will be served quickly. The second, slower. The third, slower. And the fourth, even slower, and exponentially. So on a magnetic disk, the more requests you have per disk, the more the slower you get in terms of performance. And this is very important to understand. So if you need to design a dense cluster, you just need to be mindful to the amount of concurrency workloads. Okay? 1 second. Where are we? Yes. Are you with me so far? Okay. So let's say you want to increase your read throughput. On the same example, you have 1 petabyte and 100 disks of 10 terabytes. And you want to increase your read throughput. What essentially should you do? Yes, Don, I feel like you want to say the answer. You were saying?
Your information across the disk.
That would be one option if you have magnetic disk, but if you don't alleviate the stress on each disk, you're essentially in the same problem. So let's think about it. You have 100 disks and you have 1,000 requests. That means 10 requests per disk. So what would you essentially do?
Read more sequentially and replicate data.
Let's talk about the replicate data. Replicating data, that means essentially doubling your disk space. So 1 petabyte means if you replicate, you have a replication factor of 2, that means you for each 1 petabyte worth of net data, you need to save 2 petabytes. Right?
Yep.
Okay, which is a good solution. Indeed, it will improve your read speed. What else can you do? Assuming you need to balance your costs. You have a fixed amount of budget and you're designing a new cluster. So instead of using 100 disks of 10 terabytes, try using 1,000 disks of 1 terabyte. What's the performance gain? Essentially what we did now, we alleviate the stress on each disk. Yes, Dino, please feel free to join.
Yeah, I think, I guess depending how the code is written, but yeah, it will be 10x because 10x storage.
Yes, give or take. We're talking about architectural principle. Naturally, it will differ from each workload. Okay. Let's skip this one. Okay. Just as a simple FYI, there are 3 types of file system. Whoops. There's local disk file system like XFS, NTFS, and exFAT. And there are scale out file system. What's the difference? A local file system is per server. It's not correlated, connected to other machines. Scale out file system are essentially one address space spread across several servers. It's like a storage system. This is less common, but you should know it exists. Do not be confused with fuse file system. It's a file system in the user space, which sits on top of another storage like Hadoop file system. It's essentially a file system on top of your local file system. Usually implies get set. A fuse system can also be implemented on top of S3 or GCS, but it's not designed for performance. It's only designed to retrieve small documents. So don't use that in your petascale architecture. File system example, I don't want to go too deep, but you should know that even file systems have performance gains, sometimes by an order of magnitude. For example, XFS is designed for parallelism and exFAT is designed for throughput. So if you have very extreme edge cases, this is something you should definitely look at. In terms of architectural differences, object storage works like API. It's not a file system. So the benefit is durability and scalability. It's by design, designed for parallelism. But the anti-pattern is a file system. So essentially, decoupling of storage and compute always implies object storage. On the other hand, local disk is designed for high throughput, low latency, performance, operational databases. Okay, and while Fuse is usually designed for cold storage, archive, not scalable, some custom stitches. If you talk about decoupling, it's not in this diagram explained well. It's not when you have a local disk in the same server. It's when the disk is outside. Let's talk about network. You know what? Let me even scratch that one. It's a confusing slide. Okay. Let's talk about the network, and then we'll take a break, and we'll continue our next session, okay? Network. In terms of performance of throughput, a network card, Nick is a network interface guy. What would be faster, 1 gigabit or 10 gigabit? Who wants to know, to answer this one? Don't be shy, it's not a trick question. Okay. Allow me to answer that for you. So naturally, the 10 gigabit network interface card will be faster than the 1 gigabit. However, it's not the same when you talk about a 40 gigabyte network card or 25 one, because the answer lies in the underlying hardware. In a 1 gigabyte, you have a 1 gigabyte chip. In 10 gigabyte, you have a 10 gigabyte chip. In a 25 gigabit, you have a 25 gigabit chip. But on a 40, you have 4 of 10. So essentially, your throughput would be limited to the throughput of 1 10 gigabyte chip. But you can achieve parallelism of 4. So it gives you the illusion of 40 gigabits. Why is that important? Because when you use the cloud, sometimes you fail to notice the bandwidth associated with each machine, and your data is on S3. So essentially, when you read data from your server, and you are reading it from S3, so your bottleneck becomes your network. And why is that important? Because the bigger the machine, the more bandwidth you have, but that's essentially correlated with the type of network card, and you don't always know that it's using a hardware which is combined out of smaller network cards. So essentially, sometimes you're a bottleneck to 10 gigabits and you don't know that. So you should be aware of this problem and you should monitor on that. And what's the impact of an instance in the cloud in terms of network? Usually, the bigger the instance, the bigger the network speed or bandwidth you have. So essentially, you don't need to overthink it. You just need to pick not the smallest machine, but not the biggest machine, somewhere in the middle. Now, will essentially balance you out. Should we take a break and continue our next session? What do you say?
I'm fine.
You want to continue, Miko? I'm fine.
Yes.
Yes, please.
Give me some more. Okay, guys, I'm with you to the end of the line. So let's go a little bit deeper in compression. So essentially, let's take AWS Athena as an example. You get one on database, essentially serverless, analytical DB, and you pay $5 for each terabyte scan. But the crux of it is scanned, not processed. Meaning, if you have 1 terabyte on S3 in CSV, not compressed, and you do a full scan on it, you'll pay $5. But if it's compressed, say 1:5 compression ratio, you pay only $1. Simply because Athena read a smaller file size from S3. So Athena in a way is totally decoupled because the compute is managed by AWS, the storage is managed by S3, but you have access and you control it. You cannot control the compute of Athena. So it connects well with AWS, and you can use external tables, and there's no insert time. You just put files on S3, create an external table, and essentially select format. Sounds ideal, But let's go deep into it. You have 1 terabyte of uncompressed, you select, you pay $5. The same data, only this time it's compressed on S3. You pay the $1 we discussed. This is the difference between data scan and data read. There's no insert time, but you need to be able to somehow do the processing of compression. If it's not already compressed, you need to use a thinner to do that. You can do that, but just be mindful of it. What's the benefit of compression? Should we always compress? It usually depends on your use case. In theory, compression sounds perfect. What do you mean? You're keeping less storage and you pay less on the storage layer. But what's the penalty? The penalty is on the compute. This is the storage layer, this is the compute layer. So a file compressed on S3 is essentially read to the RAM of Athena. Then you pay a penalty of compute to decompress the data, and then and only then you start the processing and showing the answer in the console. Any questions on this before we proceed?
So the previous $5 versus $1 comparison, did that take into account the compute cost as well?
Ask again, please.
So on the previous slide, you had the $5 versus $1 comparison because of compression. So you were paying $1 when the file was compressed.
Yes.
And so did that take into account compute cost as well, or was that only for?
That's the beauty of pay-as-you-go services. You don't pay for compute, you pay for data scanned. You don't care how many servers are being launched behind the scenes. That's the downside or the upside. That depends how you look at it. Where would it make sense to use serverless solutions for your processing? When you have what?
A usage that is not constant. You don't want to pay to keep servers running all the time.
Thank you, Shlomi, but let's refine that. Let's say when you have 1 terabyte worth of data, so each query will cost you, let's say, even $5, okay? But what's the underlying assumption of serverless? Pay as you go. So if you don't go, you don't pay. So if you have less jobs, less analysts, less BI queries, nobody uses the data, you pay less. Does it make sense?
Yes, of course.
Thank you. Fantastic. So let's talk about the other way around. When will it not make sense to use a serverless?
Maybe if speed is important.
Some of the serverless solutions are quite fast.
When you're handling continuously the data, I think when you're reading and you have a lot of analysts and reports and so on.
Exactly. When you have high degree of concurrency, lots of analysts, lots of jobs, lots of BI dashboards, constantly working through your pipeline, your backend, sorry. Essentially, there you want to have a flat fee kind of a scenario. Let me tell you a little secret. This is only because you've been very cooperative and you've been powering through this discussion. In some cases, serverless will be cheaper. In some cases, a 24/7 cluster will be cheaper. it's not always clear cut which is which. This is partly why you need to understand the business use case, the workload, and the underlying technology architecture and the billing structure. And then you can assess. With experience, you can narrow it down quite easily, but it requires experience. Okay? Okay.
Oh, one question before we go ahead. One question, sorry.
Please.
Yeah, so in Hadoop world, right, we have this data locality concept, right, wherein whenever we do some analysis or whenever we run a query or code, right, the code, the compute, wherever it's happening, the data node, right, it's better to have the local data, right, because it's faster. You're reading the data locally, right, now not going to the different rack and all those things, right. But now with cloud computing, there is a concept, as you were mentioning, the concept comes as compute is separated from the storage, right? So what happens to that concept of data locality, right? So that totally breaks, right? So how do you what are your comments on that?
It doesn't break.
It?
It's a simple. It's just two different types. Two types of architecture with pros and cons. I even have a slide for that, if you'll bear with me. I know you asked for a break, VK, but since you stayed with us, you stayed with us, so I'll do my best to provide a very good answer for you. So one second. First of all, you should know I had a session about EMR, Hadoop, answering all the different questions and challenges around Hadoop Spark architecture in the cloud. It's about 8 hours in the website. Enjoy it.
Oh, sure. I'll have a look at it. So is it on the Big Data Demystified website?
Yes. Yes.
Sure.
And,
I'll have a look at it for sure. Thank you for
I'm
pointing
looking
on that.
for the yes. And I'll have a look for the slide if you bear with me. I'm powering through lots of slides here. It's a very long lecture. 1 second. This is storage network. Blah blah blah. Okay, very fast. No. Yes, I think we nailed it. Haha. 1 second. I need to share that with you. 1 second. Switching slides. Don't be alarmed by my background choice. It's a default choice by Apple. Default choice, sorry. Yep. Okay. Here's that. Can you see this?
Yeah, I can see this.
So let's go back a little bit. When you have a Hadoop EMR like in AWS, if someone not familiar with EMR, just think Spark in your head, okay? And you have a locality of HDFS. This is essentially what you talked about, right? This is the recommendation. Use the EMR, use S3, and so on and so forth, correct? But the underlying assumption of the architecture, as you said, that there's a local disk and it's distributed on the Hadoop file system. So essentially, when you have a cluster of 3 machines, 3 core nodes, and you have a name node working with them, you know the name node for now, locality makes sense because it will give you better throughput, correct?
Yeah.
And it will give you more sense if the data is replicated, because essentially each file, green part, is replicated. So essentially you can double access it and double your speed of read, correct? Great. And when you lose a machine, you pay the penalty there because you need to rebalance your data all of a sudden, right? Okay, so this is the basic, and this is all the balagan that happens when you need to shuffle your data and become more and more complicated when you have more and more running jobs and production scenarios and all that. But when you talk about the other architecture using S3, by design, S3 is designed for parallelism, correct? As we mentioned. So your bottleneck becomes a network throughput between EMR cluster and your S3, right?
Okay, the throughput, right? Yeah.
Yep. So essentially, in theory, you can pay a penalty of latency to increase your parallelism capabilities. Because essentially you're not bounded by the amount of disks anymore. Does this make sense? Don't be shy. Say no, it's okay. Let's go deep into that.
Yeah. No.
It doesn't make sense. Okay. Remember my example with the 1 petabyte and the 100 disks? So it makes sense if you're 10 analysts, but what happens when the company goes to 1,000 analysts? Are you going to now all the 1,000 disks and replace everything?
No.
No, it doesn't make sense. So essentially, you want an architecture that can scale over time. So it's a matter of pros and cons, performance gain, cost versus performance. That's always your balance. And there's another aspect of the triangle, another aspect to balance. It's not only cost versus performance. It's cost, performance, and maintenance. It's a triangle.
Okay.
So this is the hidden part nobody talks to you about. Of course, cost, of course, performance, but what about maintenance? You know how much effort maintenance is required to handle a petascale Hadoop cluster? Massive. It's about 30 people with my skill set, which is, say, 20 years of experience just to make it efficient, especially in the data center capability. Okay?
Yeah, sure. I got the point. Thank you so much, Omid. It was really good.
Thank you. So let's continue.
Sorry, others for detouring. Sorry, others
Sorry?
for the detouring.
No, don't
I
apologize.
say
We're
sorry.
here for you.
Say sorry to others too for detouring. Yeah.
Yeah. Okay. So we were in the compression issue. So what I told you guys that you have also on top of the decompress issue a compress penalty. So essentially, when you read a file, decompress it, process it, and compress it back, so you get 2 penalties when you went back to this. So you should be aware of this, but as a general rule of thumb, always use compression. Just be mindful to the type of compression you choose. Anyone wants to guess why? Five more minutes and we're done. Let's power through 5 more minutes. Why should the type of compression should be a consideration?
It comes also to the performance and cost.
Performance and cost, because decompress takes time and compress takes time. So essentially, it's the time to process your data. But there's another aspect, the footprint on your storage layer. So essentially, if you have 1 petabyte worth of raw data, compression makes it either 200 terabytes in a 1 to 5 compression, or 300 terabytes, or 400 terabytes, depending on your compression algorithm. So essentially, you're paying double if you're inefficient in your compression. Does it make sense, guys?
Yes.
Oh,
yeah.
Okay. So when should you compress? The answer is always. However, pay special attention to one small use case. When your file size is small, don't do compression. It's just a penalty. Okay? Only when you go larger in your file sizes. So concluding, this is the triangle we talked about. It's always a matter of performance, cost, and maintenance. Meaning, is your job faster? Is your job cheaper? Is your job simple to maintain? This is why we talked about compression today. So we're going to stop here because I don't want to kill you, and we have lots of more slides, as you can see. The next session, we'll continue from this part, the partitioning, and I will be happy to continue working with all of you on this workshop. We're going to take as much session as needed to make everybody happy and answer all your questions. So feel free to join us for the next session. I will be more than happy to take questions now or anytime. Any questions?
So when's the next section?
The next session. Let me share my screen with you 1 second. I was just looking at that. The next session, if I remember correctly, that depends on the schedule. 1 second. All I'm doing is checking. Can you see my screen?
Yes.
Yeah.
So I'm essentially going, that depends where you are located. You'll have the same information, but I'm located in Tel Aviv. So this is part 1. Let's go to Tel Aviv. The next event of this section would be on the 13th, essentially next week. Same time, same day.
Okay. Okay.
And the next one, the week after that, and the next one, probably a week after that. No, this is past event. Oops. Bureau of future events, see all. Yes, upcoming events. Part 1, 2, 3, the next after, and part 4, again, a week after. So essentially, we'll meet every week, and if we need more parts, we'll add more parts. Does it make sense?
Yes. Thank you.
And you're welcome, and all the content will be uploaded here in data engineering architecture section. If someone interested in the EMR course, it's over here. It's free of charge over here, part 1 to 4. EMR demystified 1 to 4, 8 hours, enjoy. Okay, guys, it was a pleasure having you here. Thank you for powering through. I usually work with you guys. If you want to stop, we stop. If we want to go 3 hours, I do 2-hour session. I'm here to help. Lovely meeting you. Hope to see you again in the next session. Thank you very much. Good day.